All right, let's start our lesson. Welcome again, everyone. We're going to start our lesson. We are dealing with physical science, and what we're talking about today is organic reactions. That's all that we're going to be talking about here, organic reactions. So that's our lesson. Now, I'm going to teach you for the next maybe 20, 30 minutes. Now, I'll be slow. I want you guys to understand. If there's something that you don't get, something that you don't understand, kindly let me know. I'll be able to help you so that at least you can understand to the best of your ability. I'm going to share the screen now, and here we go. Now, when it comes to organic chemistry, we speak about a lot of reactions. The first one that you're seeing there is known as a combustion reaction. A combustion basically is a reaction between a hydrocarbon and oxygen. And this reaction forms carbon dioxide and water. And more importantly, it releases heat energy. Now, that's very important to understand, because once you say a reaction releases heat energy, you're suggesting that the reaction is exothermic. So in the reaction between a hydrocarbon and oxygen to give the products of carbon dioxide and water and the release of energy, this reaction is exothermic. You're required to know how to actually balance this reaction. So let me give you a couple of examples. Let's think of a hydrocarbon. I'll pick out methane, CH4. I'm going to react this with oxygen. That's combustion. It's going to give me two products, carbon dioxide and water, and obviously energy. Now, you need to understand that when balancing the equation, because that's what they want you to do, start by balancing the carbons first. So I have one carbon here on the left-hand side. I also have one carbon there on the right-hand side after the arrow, and that's okay. So the carbons look like they're balanced. Then I check my hydrogens. I've got 4 hydrogens here. But here, I have 2 hydrogens. So to balance this equation nicely, I need to put a 2 here. So you balance with coefficients. So you don't change the 2 at the bottom to make it 4. No, you make that 2, or you put that 2 as a coefficient. So that suggests to me that in this situation, you've got now 4 hydrogens there, just like you had somewhere there. That's fine. So I've balanced the carbons, I want to tick that. I've balanced the hydrogens, I want to tick that. Next, I balance the oxygens. So I suggest that you balance them in order. Carbons first, hydrogens next, and oxygens last. Let's look at the oxygens. On the left-hand side of the arrow, I've only got 2 oxygens, left-hand side. Then on the right-hand side, let me see how much I have. I've got these 2, that's 2 oxygens already, and then also these 2 here. So it's 2 times that oxygen. So the number of oxygens that I have here is actually 4. So to make it quite interesting and clear, if I've got 4 oxygens here, and then on the left-hand side, I have 2, to balance that, I need to put a 2, just that. So let's go through this again. What do I balance first? The carbons. What do I balance next? The hydrogens. What do I balance next? The oxygens. Okay, let me use another example. Maybe let me just keep that there, and then use another example for you so that you can see what I'm talking about. Check this out. Let's say I've got another organic compound, a hydrocarbon. Let's have methane, no, rather butane in this example, C4H10, multiplied or rather added to oxygen. There you are, and you're going to get your products, carbon dioxide and water. Just so you may know, all the time, the products of combustion are carbon dioxide and water. The reaction is exothermic, meaning that it releases, there's my statement, it releases energy. Exothermic releases energy. Let me go. So you can see I've got 4 carbons here on the left-hand side. So I've got 4 carbons on the left-hand side. I want to balance them with the ones on the right. On the right, I've got only 1 carbon. To balance that, I must put a 4, and that's fine. I've put the 4. I go further. Look at the hydrogens. I've got 10 of them. 10 hydrogens. To balance that, I must make sure that I've got 10 also on the right-hand side. But on the right-hand side, I happen to have only 2. To balance that, I need to put a coefficient, a number. That number is 5, like what you're looking at right there. Now, look at your oxygens. On the right-hand side, I actually have the following oxygens. Check them out. 4 times 2, that makes it 8 oxygens, plus these ones, 5 times that oxygen there, that makes it 5 oxygens. In total, I've got 13 oxygens on the right-hand side. On the left-hand side, I have 2. So then how do I balance it? On the right-hand side, 13. On the left-hand side, 2. I need to find a way of balancing these particular oxygens. So this is what you do. 13 is an odd number. Odd number can't be divided by 2. So you take that odd number, 13, and put it here. But make it 13 over 2. That's what you do. Make it 13 over 2. And then what does the math say for me? The math simply says this is as good as saying 13 over 2 multiplied by the 2 here. Cancel, cancel. I've got 13 oxygens. That's what basically it means at the end of the day. Now, to make it neater, like I said to you, if you've got odd numbers of oxygens on the right-hand side, so take that odd number, 13, that odd number, 11, that odd number, 7, whatever the odd number could be, 7 over 2, 11 over 2, in this case, 13 over 2. And once you do that, get rid of the 2, make it neat, make it clean, get rid of this 2. How do I do it? Cross multiply everything by 2. Okay, I can multiply this by 2. Coefficient again, 2C4H10. If I multiply this coefficient by 2, I get 13O2. Multiply by 2, I get 8CO2. Multiply by 2, I get 10H2O. You check it out properly, this definitely will be balanced. Let's confirm that together. I see the hand up. It's how I'm going to attend to you. 8 carbons. 8 carbons. 2 times 10, 20 hydrogens. 10 times 2, 20 hydrogens. Oxygens, 13 times 2. That definitely makes it 26. Let's confirm if we have 26 on the right-hand side. 8 times 2, that's 16 oxygens there, plus 10 times 1, that's 10 oxygens there. Add them together, they give you 26. And fully, it's a balanced chemical combustion equation. All right, let's have you got your hand up, and I want to attend to you right now. Right, guys, I'm not live on Facebook, but I'll put this on YouTube, don't worry. Okay, I'll put this on YouTube after this, and I'll send you the details as well. It's how you got your hand up. I don't see it anymore. So let me continue until such a time. So that's basically combustion. Write these examples, guys, and the definitions for it. Just go on to the next couple of reactions together and get this happening the best of our ability. So that's combustion is it way. I'm taking this out quickly. Let me give you 10 seconds to write this. Combustion is a very useful reaction. Let me tell you why. When you burn fuels more predominantly are organic compounds. So when you burn fuels, the burning of fuels requires therefore the production of heat, the energy. And this process of getting the heat energy from fuels is combustion. So when petrol is burnt in a car or whatever, it produces the heat, which eventually drives the engine and eventually moves the car. Taking this out, that's combustion. Let's go to the next set of equations there. Next set of reactions. Addition reactions. All right, let's move through on that one. Now, addition reactions are reactions that happen when you add into an unsaturated molecule. I need us to understand this. You've got an unsaturated molecule, and what is that? An unsaturated molecule is a molecule which definitely has a double bond or a triple bond between its carbon atoms. I need to make this clear. It's unsaturated. Why? It's got a double bond or a triple bond within the carbon atoms. Addition reactions only happen when your particular organic compound is unsaturated. So you only add on unsaturated organic compounds. In addition, the double bond or the triple bond is broken. Then you add into it. If you look at the definition that you're seeing there, it says an addition reaction is a reaction in which an atom or molecule is added to an unsaturated molecule, making a single product. Let me try and illustrate this. Addition. You've got an unsaturated molecule, A, and then I'm going to add another molecule or an atom, B, and I'll end up forming a single compound, C. So in other words, I've added B to A. And why is addition possible? It's because A has a double bond between the carbon atoms, or A has a triple bond between the carbon atoms. So we're going to go through a number of organic compounds, right? A number of addition reactions, whereby we show that we're adding into an unsaturated organic compound, and therefore we're going to form a single product. Let's go to our first one there, all right? I want to move. Right, our first one is this one, halogenation. Halogenation is an example of an addition reaction. So what do we do when we are halogenating? We are adding a halogen to an alkene to make a haloalkane. Okay, alkene, that's double bonds between carbon atoms. What do I do to it? I add a halogen into an alkene, I will form a haloalkane. Haloalkanes have another name. The other name for haloalkanes is alkali halide. So if you read in some books and they say alkali halide, please know that they are talking about a haloalkane. So halogenation basically is the addition of a halogen to an alkene. Now you need to understand what halogens are. Halogens are group 7 elements in the periodic table. So halogens, we're talking about elements such as chlorine or bromine or iodine or even fluorine. So an alkene plus a halogen, chlorine, bromine, iodine, fluorine. If you add an alkene to a halogen, you're forming a haloalkane. Let's use an example. Let's have an alkene, right? Now, we can have it this way, an alkene, let's have it this way. Okay, people are still coming through the platform, so kind of disturbs my flow, but I will pull through somehow. Okay, alkene. Let's have propene as an example. Propene has got 3 carbons, okay? I'll put a double bond here, and then maybe on the other flip side, I'll put my hydrogens there. There you are. Remember, around every single carbon atom, there must be 4 bonds. So there you are, hydrogen, the hydrogen there, my hydrogen there, my hydrogen there, that one there, and that one. I'm going to add a halogen. Halogens are diatomic. Diatomic means that it's Cl2, two atoms in chlorine, Cl2, Br2, I2. Let's add bromine as an example, Br2, like that. Now, I need you to understand something here. So because addition happens between the double bond is broken, okay? So the double bond is broken. And what happens when the double bond is broken? You're going to add the bromine, Br. There are 2 BRs in this case. So I can add a BR there. So there's my BR there. I can also add another BR there. There's my BR there. So I've added 2 of those BRs. You can write this a bit neater this way. Let me show you what you can do, all right? So you can always do it this way. There's my BR like this. So that's all pretty good. So you can write it simple like that. That's BR, as you can see. So this becomes an alkene reacting with a halogen to form a haloalkane. When we start doing questions, we'll come back to these things and be able to name them. But for now, just know that this is a haloalkane. This reaction is very important because this reaction is able to differentiate between alkenes and alkanes. Or rather, to be specific, this reaction, halogenation, is very important in differentiating between unsaturated organic compounds and saturated organic compounds. Unsaturated organic compounds, you can add into them. Unsaturated, you add, but saturated, you can't add. When I go further with the lesson, I can tell you can substitute into them or you can eliminate. But for now, to differentiate between an alkene and an alkane, a saturated and an unsaturated organic compound, you can use halogenation, particularly when you use a substance known as bromine water. All right, let me explain. Let's say you've got 2 substances, A and substance B. You don't know if A is unsaturated or saturated. You don't know either for B, whether it's saturated or unsaturated. You just don't know. You want to find out between the 2 who is unsaturated. Let's react A with bromine water. Bromine water is reddish brown in color. So it's like reddish brown in color, bromine water. Now, when you react A with bromine water and the bromine is decolorized, all right, that's a very important thing. You react A with bromine water and bromine water is decolorized. Then it means to me that A is unsaturated. So let me get this clear. Unsaturated organic compounds, when you react them with bromine water, they decolorize bromine water. If B, I react B now with bromine water and there is no change at all, no change in the particular color, it means B is saturated. So keep in mind, halogenation can be used as a particular reaction to differentiate between unsaturated and saturated organic compounds. If it is unsaturated, bromine water is decolorized from reddish brown to colorless. If it is saturated, single bonds between carbon atoms, the color does not change, so you can differentiate and see who is unsaturated, double bond, triple bond, who is saturated, single bonds. In every reaction, you must know the condition. I put them right there for you. I say the reaction condition. If you look at this properly, I put the reaction conditions here. I said you add Cl, Br, or I, or add X2. So that's halogenation right there. All right, let's go to the next one. The next one is known as hydrohalogenation. Hydrohalogenation. Let's get this clear now. So the names are pretty easy to memorize because the names actually speak about the actual reaction itself. So you've got alkene reacting with water in the presence of an acid there. I think, let me just sort this out here. I think this is, let me sort this out here. Right, let me explain with this. It's not hydrohalogenation, this should be hydration. I think there was a mistake there. Hydration, I'll come on this one there. Let me speak about hydrohalogenation. Let me just cancel this off for now. Now, in hydrohalogenation, you are adding an alkene, there you are, to a hydrogen halide there. and you're going to form a haloalkane. There you are. So you add an alkene plus a hydrogen halide, you're going to form a haloalkane. All right, let's do an example. Let's use propene. So I've got 1, 2, 3. And I'm going to put the double bond right there, as you can see. And then I'm going to add a hydrogen halide. An example, HBr, as an example. You can add HCl, that's also a hydrogen halide. You can add HI, hydrogen halide. You can add HF, hydrogen halide. Here's the rule. When addition happens, it happens on the carbons in the double bond. All right? The hydrogen, get this clear. The hydrogen from hydrogen bromide in this example will add onto the carbon in the double bond already containing the most number of hydrogen atoms. Let me say that again. The hydrogen, okay, hydrogen where? The hydrogen in hydrogen bromide, this hydrogen, will add onto the carbon within the double bond that already contains the most number of hydrogen atoms. So if I compare this carbon here and that carbon there, I notice that this first carbon already has 2 hydrogens. And my statement says the hydrogen from hydrogen bromide will attach itself to the carbon in the double bond that already contains the most number of hydrogen atoms. In other words, this H will go right here on this carbon. Why? Because this carbon is the one that already contains the most number of hydrogens. Check it out. This carbon has 2 hydrogens, while this carbon only has 1 hydrogen. So the H goes to the carbon in the double bond containing the most number of hydrogen atoms. The Br on the flip side, now Br here. The Br on the flip side goes to the carbon in the double bond that contains the least number of hydrogen atoms. So the Br makes its way to this particular carbon. Why? Because it's the carbon with the least number of hydrogen atoms. It's got only 1. So then my structure can become like this: 1, 2, 3. What do I know? There's that one there, it was 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 there. So what did I add? I added a hydrogen there. What did I add? I added a bromine there. And that becomes a haloalkane. The other name again for it is known as a hydrogen, as an alkali halide. So please make sure that you get this right. The H goes to the carbon in the double bond that contains the most number of hydrogens. The Br goes to the carbon in the double bond that contains the least number of hydrogen atoms. Write this down. I want to move on to my next reaction. Take this out and move on to my next reaction right there. Write this down as quickly as you can, family. Remember, this is hydrohalogenation. Hydrohalogenation. Let's go to our next one. Taking this out. Let's go. All right. Okay. Hydration. Let's go to hydration. Properly done. Hydration. So hydration makes its name quite clear. When you say hydration, you're pretty much talking about the addition of water. So an alkene, if you add water onto it, it gives you an alcohol. Okay, so hydration is the addition of water to an alkene. If you notice, I'm only using alkenes, though I said it clearly that addition reactions are considering alkenes and alkynes, considering double and triple bond. But for your level right now, you deal with alkenes when it comes to addition reactions. So an alkene plus water in the presence of an acid catalyst will give you an alcohol. The name of that reaction is hydration. Let me give an example. Let's use propene again. It's easier to make you understand using propene. There we are. I'm going to have this way, the double bond there. There's my reaction right there. What am I adding? I'm adding water. Let's write it like this. So when they ask you in the exam to write this in structural formulas, don't write water as H2O. No, that's not a structural formula. That's a molecular formula. Structural formula is this one that I just wrote there. So you must show the bonds happening between the H and the O and the H. So this is a structural formula. What am I adding? Water. Who's going where? Obviously, the H will make its way to the carbon in the double bond that already contains the most number of hydrogen atoms. That's okay. The OH, there we are, will make its way to the carbon in the double bond that contains the least number of hydrogen atoms. So the OH will make its way somewhere there. And so I can draw the structure now. I see your hand, Babalo, and I'm going to deal with you now. Like the OH will make its way to the carbon again, which contains the least number of hydrogen atoms. So here's my structure. Here's my structure. So I'm going to have 1, 2, 3. Let me see what I had. I had this, I had that, I had this, I had that, I had that, I had this. What did I add onto this? I added an H, there you are. I added an OH, there you are. Where did I come from? I came from an alkene, and where did I end up? I ended with an alcohol. And what are the conditions for this hydration reaction? I need, number one, excess amount of water. That's fine, makes sense. I'm adding water. What else do I need? I need a catalyst. Remember, the presence of a catalyst ensures that the reaction occurs faster. So I need a catalyst. And what is the name of the catalyst? I can use sulfuric acid, and this is its formula. I can use phosphoric acid, and this is its formula. So when we do questions, please be clear. When we do questions, if they ask you the name of the catalyst, write the name. If they ask you the formula of the catalyst, write the formula. You must know all these things. Name, formula of catalyst. It could be sulfuric acid, or you can also use phosphoric acid. These reaction conditions, people, are very important, as you can see. All right. I don't know if you guys must be, I don't know if you guys are making mistakes here in terms of lifting up your hands, because you lift up your hands and you put that down. So it's fine. Let's keep going to the next one. I'm on my next one. So that's hydration. Let's go to the next one. Hydrogenation. Hydrogenation. Hydrogenation is another example of an addition reaction. In hydrogenation, you're simply adding a hydrogen to an alkene. Interestingly, when you add hydrogen to an alkene, you form an alkane. I'll put it for you here, and it makes a whole lot of sense. So alkene plus hydrogen gives you alkane. This reaction happens in the presence of catalysts. You can choose either of them. PT, platinum, I'll put it there for you. Ni, nickel, I'll put it there for you. PD, palladium, I'll put it there for you. So I'm simply saying to you, this reaction happens in the presence of a catalyst, a metal catalyst, which could be platinum, nickel, or palladium. You are coming from an alkene to an alkane. Let's make it clear. You're coming from unsaturated to saturated. Let's make some sense. Let's use an example. Propene again. 1, 2, and 3. There's my double bond there. Obviously, I can add into this. Hydrogen is diatonic. That's hydrogen there. is diatomic. Okay, let's put it like this. I think it will make sense. Structural formula of that. Then notice the following. I'm going to add onto this structure, but because I'm adding the same guys, H and H, doesn't really matter where the H's go because it's just H. So at the end of the day, here's what I'm going to have. Okay, hold on to this. So I have what I have this, I have you, I have you, I have you, I have you, I have you. What did I add? A hydrogen. What did I add? A hydrogen. So what's happening? From an alkene to an alkane. Let's be specific. From propene, the name, plus hydrogen to propane. I know I'm sounding funny, but you need to express that way. So propane, hydrogen, propane. All right, let's keep working. Look at the conditions. I say to you, there must be a catalyst. There must be the alkene dissolved in a non-polar solvent, and obviously it must happen in the presence of hydrogen. This reaction is important in the food industry. Why? Because it is the one that forms margarine. When margarine forms, any type of margarine out there, when it forms, it's coming from unsaturated plant oils. To harden it, you need to hydrogenate those unsaturated plant oils. In other words, you must react those unsaturated plant oils with hydrogen in the reaction of hydrogenation. That's the reaction itself. Now, I'm done with addition reactions. We're now left with two types, and then after this, we'll do a lot of questions together. So, hydrogenation is part of addition. So those were addition reactions. Just to summarize this family, listen to this. Addition reactions, where do they occur? They only occur on unsaturated organic compounds. Fine. Where does addition take place? Addition takes place on the double bonds, on the carbons within the double bonds. So addition strictly happens between the carbons in the double bonds. Don't forget that. Let's go to our next set of reactions. Someone's got a hand up. There you go. Babalo, I've unmuted you.
Yeah, finally, sir. Thank you. So I wanted to ask, what are the reaction conditions for hydrohalogenation?
For hydrohalogenation, well, there's not really much to do with it. There's not much on hydrohalogenation, which I think is this one that you're asking me about. There's not much except that, because I need to cancel this off, this was wrong right there, except that no water must be present. In other words, they say in hydrohalogenation, the conditions must be anhydrous. Or you can say no water must be present. But pretty much this reaction happens almost anywhere with any temperature. But just note that no water must be present. That's just basically it. All right, thank you so much for that one.
Thank you, sir.
Linde KH, I think that's Linde. Go ahead.
Sir, I wanted to ask you, why is it that the no water must be present? Is it because of if there is water, is it going to be alcohol?
Yes, in the presence of water, and especially if there's a lot of water in that particular situation, it will end up being an alcohol because it will overcome the fact that there's now a lot of water in comparison to the hydrogen halide. So that's why it must happen in the presence of, or in the absence rather, of water. That's why you should have it like that. You don't really get such questions in the exam, but you must just know that for every reaction, there is a condition. Now, I must make a disclaimer. Not all reactions have conditions, not all of them. Most of them do. So whenever I don't mention any reaction condition, it's probably because it's not really there, or this reaction can happen in almost any environment. All right, beautiful, and thank you for that. Elimination reaction. Let's go to the next set. Elimination reactions, guys are wonderful. Thank you for that. I'm hoping to be done within the next 20 minutes or so. I was hoping I'll be done earlier, but fine. Let's keep learning so that at least if we're clear on everything, we can be at least able to answer our questions properly. Elimination. To eliminate means to remove. In other words, I'm taking something out of a compound. So that's why I said an elimination reaction involves the removal of adjacent atoms from a molecule. Now, when you eliminate from a particular organic compound, when you take out adjacent atoms. Now, I need you to listen to the words. It says adjacent atoms, that's plural. You're not taking out one thing, no. You're taking out at least two things. You're removing adjacent atoms from a molecule. This removal results in the formation of multiple bonds, usually double bond, and the release of a small molecule. So that's why they are called elimination reactions. All right, here's what happens in a typical elimination reaction. I'm going to use the first one, which for me would be dehydrohalogenation. Dehydrohalogenation. Let's explain that. In dehydrohalogenation, you are removing a hydrogen and a halogen from a haloalkane. Let's get this right. Elimination, the removal of adjacent atoms. So in dehydrohalogenation, you are removing a hydrogen and a halogen from a haloalkane. You're going to form three products: an alkene, a metal halide, and in that case again, in water. Let me use an example of all of this so you can see what I'm talking about here. Makes it clear. Now, dehydrohalogenation. Let's have an example. Let's use something with bromine in it, a haloalkane with bromine in it, and I'm just going to draw the structure for you here. So I'm going to have it as 1, 2, then I'm going to have it as 3, then I'm going to have it as 4. All right, then I'm going to have add my hydrogens. Guys, in the exam, I'm just using this as examples. In the exam, please make sure that you put your hydrogens, your H everywhere. I'm just using these strokes, these lines as examples because I don't want to waste time writing H everywhere. Right, so I'm going to have a BR somewhere there, and then I'm going to have an H there. Then I'm going to just put that H there. Right, this is a haloalkane. What do I want to do? I want to dehydrohalogenate. What is dehydrohalogenation? It is the removal of a hydrogen and a halogen from a haloalkane. Let's remove. Let's eliminate. So here's the key. The question is, I'm going to remove a halogen. No problem. There it is. But which hydrogen am I going to take out? Is it the one on the right-hand side of the halogen or the one on the left-hand side of the halogen? Now, I need to introduce you to something here. When you dehydrohalogenate, you're going to form two products. One of them is called a major product. The other one is called a minor product. You will form two products when you dehydrohalogenate. Major product, minor product. So what do I know? The major product is formed when you take the Br halogen and the hydrogen on the right-hand side of the Br. Major. Br, yebo, and the hydrogen on the right-hand side. What do I mean? Check this out. This is a rule, by the way, okay? These are rules, right? So I'm going to take out this Br, okay? And then who? The H on the right-hand side. So look at this. What's my product? There you are, okay? I need to make this clear. All right. Let's see. I heard you. I heard you. I have you. I heard you. I heard you. I heard you. I heard you. So what did I do? I heard you as well. Now, what did I do? I removed the BR, gone. What did I do? I removed an H. So these guys are gone. I eliminated them. What do I put in between? I put a double bond. Hence, when I spoke about elimination, I said it's the removal of adjacent atoms and then the formation of multiple bonds. So between the two carbon atoms now, where you removed, you put the double bond. So where you remove is where you put your particular double bond. Plus, we go on, the metal halide. Now notice something. I said you use a strong base. Strong base. So in dehydrohalogenation, you use a strong base. That base can be sodium hydroxide and potassium hydroxide. But here's the key. I need you to understand that the base must be concentrated. It must be a concentrated, strong base. So the reaction conditions for dehydrohalogenation tell me that my haloalkane must react with a strong base. And when it does that, that base must not just be strong, but it must be concentrated. So there must be my sodium hydroxide. Let me put sodium hydroxide as an example there. Metal halide, right? The Br has been removed, okay? And the Br will react with Na to form NaBr. That's the metal halide. And then water, how come? There is H that has been removed, okay? That H goes to react with OH from the strong concentrated base and is going to form water as well. So you need to understand this particular reaction, dehydrohalogenation. Let's go through it one more time. What am I removing? A hydrogen and a halogen. What do I make? A major product. What can I make? A minor product. So what example did I use now? Major. What happened? I took out the Br halogen and the H on the right-hand side. They're gone. What do I replace with? Where I took out, I replaced with the double bond. There you are. I've replaced with my double bond there. And then what happens next? I get a metal halide. How come? Well, the Br will react with Na, sodium bromide. The H will react with OH to form water. So this one is my major product. So the question in your minds now is, what is the minor? Very simple. The minor product is formed when you take out the Br and the H on the left-hand side, right? So I'm taking out the Br, there you go, and the H on the left-hand side. So my minor product becomes this one. Check this out. All right, there you are, there you are, there you are, right, there you are, and then there you are, there. I've put a double bond there, and you have something like this right there, and then something like that. That's my minor product. The Br is taken out, and the H on the left-hand side. Dehydrohalogenation. So when I say the reaction conditions, there must be a concentrated strong base. I also need to tell you that there must be heat, and you must heat under reflux. I explained that. Heating under reflux is like heating a container or heating in a container which is closed. So the vapors, you don't allow the vapors to escape. So they condense within, return to the reaction vessel during heating. That's what it actually means, heat under reflux, and that's dehydrohalogenation. Let's go to our next one quickly on that one. All right, I'm going to go to the next one, which is dehydration. Right, dehydration. If there are any questions, again, just lift up your hands, and I'll be able to read the messages later on, so that at least I can be able to pull through. Amali, you got a question there? There, I've asked you to unmute you. Go ahead.
So, in what situation would we have to maybe replace the single bond with a triple bond instead of a double bond?
For your level, which is grade 12, we don't deal with that situation. So we don't deal with coming from haloalkane into something with a triple bond. So you'll notice I made a disclaimer earlier that you only deal with double bonds and single bonds just now when it comes to organic reactions. So it will be unfair to teach you how you actually do it, especially knowing that it's not going to come out in the exam. So basically, for your level, it's just from either single bonds to double or from double to single under this particular topic. All right. So that's what happens
Okay,
right
thank you,
there.
sir.
All right. Beautiful. Now let's keep going. I'm going to my next one. Okay. 2 people raise their hands, and that's Ubongi. Right. Okay. Let's have Bongi coming through. Go ahead.
Okay, I think I missed you there on dehydrohalogenation. You said it is the removal of what and what and what?
It's the removal of a hydrogen and a halogen from a haloalkane. The names pretty much sell themselves away. Hydro, you're gone. Halogen, you're gone. Dehydrohalogenation. The removal of a hydrogen and a halogen from a haloalkane. Thank you so much for that one. You guys are wonderful. Let's keep going to make sure that everything of ours is proper and good. Okay, next one, dehydration. Dehydration is basically the removal of water from an alcohol. So we remove water from an alcohol. Let's have an example of that one. Alcohol, 1, 2, 3, and then 4. Let me put an OH somewhere there. That's okay. Let me put an H there. Let me fill up my structure with that. Remember, guys, alcohols contain the hydroxyl group, the OH group. Alcohols contain the hydroxyl group. In this reaction, it happens in the presence of an acid catalyst, most importantly, sulfuric acid. So you must have a catalyst, and that catalyst is sulfuric acid mostly, right? It happens at high temperatures. Please note that when you're dealing with the reaction. What am I removing? I'm removing water. I am dehydrating. Let's make it clear. The OH must go, and the H on the right-hand side must go. I form my major product. All right. So when I remove the OH and the H, what do I replace by? A double bond. And what do I form, or what do I have as well? I have water that comes out from that particular reaction. As you can see for yourself, I've got an alcohol and I'm removing water from it. This becomes my major product. Now, if I want the minor product, I said it to you guys, family. I said you remove the OH and the H on the left-hand side. So I'm going to remove this guy, and then I've got 1, 2, 3, and then 4 right there. Then I'm going to have that. I heard you, double bond there. OHH has been removed. This forms an alkene from an alcohol, dehydration, and these are the reaction conditions. Major, minor. In the exam, they ask you for the major product, mostly major product. Let me just give an example of something. I know someone probably is thinking about this. Let me give an example. So in the exam, they usually ask for the major product. So they specify, write down the structural formula of the major product, blah, blah, blah. Right. Let me give an example of something here. Let's say you've got a situation like this. You've got my OH here and my H there. And they ask you to write the major product. Obviously, there is no H on the right-hand side. Nothing. It's not there at all, right? Also on the left-hand side, it's not there at all. The H there. So basically, you take this out, and then you put a double bond in there. That's all that you do. So you take that out and just put a double bond in there, and that's fine. You rarely get questions like this, but they may come out in the exam. So let's just prepare ourselves for anything on that one. So again, this reaction is known as dehydration. Okay, let me go back to my original one in case someone was writing this like that, like that. That's my original one. That's the major. I just want to write the minor. I'm removing the H and the OH there, but the OH will be now the one that I removed. Let me just remove this. There is gone. There is gone. Is the H on the left-hand side. And I form water, and those are the conditions. All right, that's dehydration. Let's finish this up Let's go to the next one there. We're going to our last set of reactions. Then after that, we go do questions. All right. Taking this out. There we go. All right. Now, in elimination, we also have another reaction, cracking. Cracking is an example of an elimination reaction, cracking. Right. It's defined as the breakdown of large saturated hydrocarbon molecules into smaller, more useful compounds. Those compounds could be saturated or unsaturated. Let me say this again. Let me go through this again. Listen to me. What is cracking? The breakdown of large saturated hydrocarbon molecules into smaller, more useful hydrocarbon molecules, and those smaller, more useful hydrocarbon molecules can be unsaturated. So you've got a large organic compound, large. Break it down into smaller, the key word is useful. Smaller, more useful. Here's an example. Here's an example of all of this, right? I see hands are up. Here's an example. I have a large compound. Let me start with this one. Looks a bit nicer. There, C10H22. I'm going to break it down into this and also into that. So this is cracking, breakdown. And cracking can happen in two ways. There's what is called thermal cracking, which uses high pressures and high temperatures. Thermal heat, high pressure, high temperature. There's another type which is known as catalytic cracking. Mostly it uses a catalyst in the presence of low temperature and pressure. I need you to see the math of cracking. I have 10 carbons here. I've cracked them into 8 carbons there and the other 2 there. So 8 plus 2 still gives me 10 carbons. I have 22 hydrogens. I've cracked them into 22 as well on the right-hand side. But how? I broke down 18 and then the other one is 4. 18 plus 4 is definitely going to give me my particular 22 hydrogens. So in whatever you do, break them and make sure that they balance. The carbons on the left must balance with the carbons on the right. That's cracking. Look at another example. This one here. Right? This is actually octane, an unsaturated hydrocarbon, and you're breaking it down to this one, C5H12, which is pentane, and C3H6, which in this case will be propene. And I made it clear. Listen to me. I said when you break down that large hydrocarbon molecule into smaller, more useful. Those smaller, more useful can be unsaturated. They also can be saturated, just like the second example that I'm alluding to here, right there, as you can see for yourself. So remember, cracking, and I'm reading the definition, is a reaction in which large saturated hydrocarbon molecules are broken down into smaller, more useful hydrocarbon molecules, some of which are unsaturated. 2 types of cracking. Thermal cracking. What do I use? I use heat and high temperatures. What else do I have? I have catalytic cracking. What do I use? I use low temperatures and pressure, but more importantly, I use a catalyst. Catalytic cracking, thermal cracking. Again, it's part of elimination reactions. Right, let's go to the last one on elimination. It's a very interesting one right there. Okay, I saw 2 hands that were up. I'm not so sure if they're still up there. And then Gladys, let me start with you.
Thank you very much, sir. I just was asking the question for dehydration. You made an example if our OH is in the first carbon. So I wasn't sure if I got you correctly with regards to our major and minor product. May you kindly please repeat on that, sir?
Okay, no problem. I'm on the screen under dehydration as well. I'm going to come through now and just explain that. And they are saying to you that if you've got something like this, let's say the OH is on the first carbon, it's definitely is a primary alcohol in this case, and the H and there. In this case, you're only going to have one product. There's no major or minor in this case, because I can't take, there's no H on the left-hand side. There's no H. There's just an H on the right. So all I'm simply going to do is I'm going to remove this OH and H, and my product at the end of the day would be like this. There's my double bond. Those are my single bonds there, right? They are, and maybe something like that. So that's all that you're probably going to have at the end of the day. There is no two products here. Again, I need to make it clear. You're usually asked about major product. That's what you're usually asked. That's always the concern. Major product. So you take out the OH and the H on the right-hand side, that's your major. If there's an H on the left-hand side, that will be your minor in that aspect. Okay, thank you so much for that one. Let me just make a couple of hands there that have come up. Let me start off. Okay, I'm going to just lower down ladies' hands so I don't get confused. Olheng, that's you next. Go ahead.
Hello, sir.
I can hardly hear you. Go ahead.
Can you hear me, sir?
Yes, now I can hear you. Go ahead.
Okay, sir. With dehydration, sir, when you did your example, your double bond was on the second carbon. So, sir, when we do hydration, right, the first H will choose to go where there are more H atoms. But now, sir, when you're doing your example with dehydration, your double bond is now on the second hydrocarbon, on the second carbon. Why is it not on the first carbon?
Okay, let me do an example of this. Okay, thank you for that. Let me do an example. Let me go back to hydration. Look at this. Alkene, let me use this because in hydration I used propene. But let me come through to this. Let me put a double bond there, and then that, and then that, and then that. Right. Okay, then I'm going to add water. I'm using the structure of, I'm talking about hydration. And now in hydration, I'm using a different example. Okay, so the H goes to the carbon within the double bond that contains the most number of hydrogen atoms, right? And then let me see if I did this right. 1, 2, 3, 4, 1, 2, 3, 4. Right. So your question is based on the example that I used, where I was using, I think I was using propene for hydration. And then I also used, butene, or rather butanol, or butane 2-ol to be specific, for dehydration. Let me show you from here. This will make sense. People are still coming through, so I'm having a bit of a problem with the administration part here. Let me take this out, maybe to make a bit of a clear example if I use propene again. Let me have it like that, like that. Let me remove that, and let me put the H there. I was saying to you, this H will travel to this carbon because it contains the most number of hydrogens. And this OH will come to this top carbon here, right here, because it contains the least number of hydrogens, this OH. All right, let's have our structure. There. Okay, I've added. Right. Let's remove. Because you see, hydration and dehydration are opposite. In fact, when you're dehydrating, you're removing water. When you're hydrating, you're adding water. So these are actually opposite reactions. Let's dehydrate using this same example. Let's go backwards. What am I removing? OH. What am I removing? H. Where? On the right-hand side. Gone. I'm removing this. Let it go. It's gone. It's removed. What do I replace by? Double bond. And I have this exact structure the way I had it in the beginning. So these are basically opposite of each other. And so in that example, I had used, I think I'd used butane or butane 2-ol, and then in this example, I just used propane, but still it comes out to the same thing at the end of the day, right? So when I do a question, I have a question like that anyway, that I'm going to deal with, and you'll see what I'm talking about probably when I get to that question. I actually want to hurry through and do a lot of things together here. All right, let me move on quickly. I don't know if anyone else has a hand up. Oh, yes, there is. Let me just go to our next one, Cupid. Cupid, go ahead. I've unmuted you.
Sir, thank you very much, sir. Can you hear me?
Now, loud and clear now, yes.
Yes. I was saying, can you kindly repeat the process of cracking? I didn't quite get that.
Okay, so you want me to repeat the process of cracking?
Yes, sir.
Okay, cool, no problem. Let me just go quickly on that one, on cracking. All right, don't worry, guys, we'll finish this through now and get down to understanding more things. Cracking. Now, in cracking, all I was simply saying is that you are breaking down a large organic compound into smaller, more useful organic compounds. So you've got this compound here, you break it down into this and also into that as well. So you look at what's happening. Let's go step by step. C10H22 is big, make it small, break it into, in this case, I put two organic compounds. I put C8H18 and C2H4. I wanted you guys to understand that when you balance the carbons, it's always clear they must be the same. There's 10 carbons here, there's 8 here, plus the 2 there. There's 22 carbons here, there is 18 there, plus the 4 there. That makes it into 22 as well. So basically speaking, all you're simply doing is you're breaking down a large organic compound into smaller, more useful organic compound. That's just cracking. And there are two types, which is catalytic as well as thermal cracking. Allow me to move quickly, guys. Daniela, I see your hand. Allow me to just finish this up, then I'll come to you because I think my time is really moving quite fast, more than I had anticipated. Right, let's go to esterification very quickly. Esterification, believe me or not, there's an example of an elimination reaction. Esterification is the reaction that forms an ester, right? An ester is formed when you react an alcohol, okay, plus a carboxylic acid there. That's how you form an ester. And also this reaction removes water. That's why PROD is part of elimination. So here are your products, an ester and water. The conditions is that there must be heat and there must be an acid catalyst, and that acid catalyst is sulfuric acid. Okay, alcohol. Alcohol, this is an example. Let's use propane or propanol. Let's go 1, 2, 3. Let me put the OH here. Propanol is an alcohol, right? I'm using that example. I'm writing the structural formula. Let me use the carboxylic acid as an example. Let me use butanoic acid. But means 4. 1, 2, 3, 4. Please note, guys, this topic that I'm doing with you today is part 3 of a topic called organic chemistry. So this is just part 3, organic reaction. So some things already have been done before. You need to probably have an idea of that. Now listen to me. I want to form an ester. An ester is formed from esterification. Esterification is a reaction which is part of elimination reactions. Produces an ester and water. Esterification comes when you react an alcohol and a carboxylic acid. So how is my ester going to be formed? Break it down. Here's the easiest way to remember this. When drawing an ester, start by drawing the number of carbon atoms from the alcohol. I want to specify. Start by drawing the number of carbon atoms from the alcohol. The alcohol is propanol. That's the name. The carboxylic acid is butanoic acid. That's the name. The ester must start by having the number of carbon atoms from the alcohol. Then what? Put what I call the bridge. The bridge, which is an oxygen. The bridge. Don't forget that. 3 carbons from where? From the alcohol. The bridge. After the bridge, how many carbons? Write the number of carbons from the carboxylic acid. butanoic acid. So how many carbons do I see from the carboxylic acid? 4. 1, 2, 3, 4. After the bridge, write them 1, 2, 3, 4. Then what? The first carbon after the bridge, put a double bond oxygen. First carbon after the bridge, put a double bond oxygen. Then fill up the rest of your structure with your hydrogens, noting that around every carbon atom, there must be 4 bonds, plus water, the one that has been eliminated. This is esterification. How do I draw my ester? First 3 carbons from the alcohol, the bridge. After the bridge, 4 carbons from the carboxylic acid, and then the first carbon after the bridge, double bond oxygen, fill up the rest of your structure with your carbons. Water has gone out as well. Esterification. Let's give the name of the ester. Name of the ester. The name of an ester is a 2-part name. 2-part name. It incorporates the alcohol part and the carboxylic acid part, and it ends with OAT. OAT, let's give a name. Alcohol part. Propyl. Then you leave a space. Carboxylic acid part. Butanoate. Propyl, butanoate. Propyl, propanol. Butanoate, butanoic acid. So just by reading the name, you can actually tell who makes the ester. Just by reading the name. Propyl, butanoate, okay. The alcohol, propanol. The carboxylic acid, butanoic acid. Esterification. Now let me make something clear here. Esterification is probably the only reaction in the lab which produces a substance which has a pleasant smell. This is why esters are used in the cosmetic industry, in the food industry as flavorants. So when it's written banana flavor or apple flavor or nut flavor, those are esters of that. They smell like nuts, they smell like bananas, they smell like apples. They are used in the food industry. So our perfumes, our lip gloss, the things that we use that smell nice, our roll-ons, colognes, whatever, they're all made from esters. These are made from an alcohol and a carboxylic acid. The reaction is esterification. And on the left-hand side of the corner, I put down for you the reaction conditions. There must be an acid catalyst, sulfuric acid, there must be heat. Please note how popular sulfuric acid is as a catalyst in almost all the reactions. It's almost there everywhere. Sulfuric acid, H2SO4. All right, I want to move on to my next things there. I'm about to finish up my lesson. Then we can now start to do a couple of questions together. I saw the hands, I'll attend to them. Allow me to move on. I want to take this out in the exam, family, in exam. This what I've just written here could be as good as 7 marks. Structural formula, 7 marks. You could get this as far as 7 marks. So make sure that you know it and understand. I'm ready for my next one. Okay, we're going to the next one there, the next set of reactions, substitution reactions. Right, I'm going to just go through 3 of them. They're very easy to understand and quickly, time permitting, we can do at least 4 questions all together as a family. Substitution. So a substitution reaction is when you remove a certain molecule from an organic compound and put another one inside. So there's substitution. So this is a certain molecule, and then I want to take this one, and in the place of this one, I want to put that one. And then in the place of this one, where that one was, it goes back to the other one. I'm hoping you can see the sense that I'm trying to do. Right, I'll show you this when we start doing an example. But in essence, all you're simply doing is you are replacing a certain atom with another, or a certain group of atoms with another. That's all you're doing. You're replacing in that. So it's substitution. All right, let's get this clear. Here's an example of substitution. The first one is called hydrolysis. Now, hydrolysis is very interesting because hydrolysis looks very similar to dehydrohalogenation. Very, very similar to dehydrohalogenation, but it's not dehydrohalogenation, it's hydrolysis. Here's an example. Let's say I've got a haloalkane, okay? Haloalkane. So 1, 2, 3, and then 4. Let me just do this here, like that. And then I'm going to add a dilute base. Dilute base. Base could be sodium hydroxide. There you are. And then I'm going to form an alcohol. What happened? Notice then, let me put a BR there. Notice that the OH will go and replace the BR, substitute. And the BR goes to where there was the OH. So you're going to have a situation like this at the end of the day, where there was BR, there's no longer BR, there's now OH, like that. And then where there was OH, there's no longer OH, there's now BR, metal halide, NBR there. Now here's the key, listen to me very carefully. In hydrolysis, you're always going to use a dilute base. And you have mild heat as well. Now, I say to you, this reaction is substitution, very similar to dehydrohalogenation. Let me go back to dehydrohalogenation as an example. Same thing, same thing. 1, 2, 3, 4, right? BR, and then H there, then that, and then that. There you go, there you go. And again, it's sodium hydroxide. But when I spoke about dehydrohalogenation, I made it clear that the sodium hydroxide must be strong and concentrated. So when it's strong and concentrated, you're not going to get an alcohol. No, you're going to get an alkene and a metal halide and water. Let me show you. Remember, in dehydrohalogenation, major product, Br and H on the right-hand side. We go 1, 2, 3, 4. Double bond there. They are. And maybe let me just put this. They are. Plus Ru, plus NaBr, plus Ru, plus H2O as an example. So this one uses concentrated. Now, I want you to see. You've got the same reactants here for both reactions. Same. What's the difference? Dilute. What's the difference? Concentrated. So it looks like when you react a haloalkane with a dilute base, you're going to undergo substitution. The name of the reaction is hydrolysis, and you're going to form an alcohol. Dilute base. If you react the same thing, but this time with concentrated, you're going to get an alkene. The name of the reaction is dehydrohalogenation. You're going to form sodium bromide in this example and water as well. So in terms of what type of product you end up forming depends on whether the base is concentrated or the base is dilute. Dilute base in a haloalkane, I hydrolyze. Concentrated base in a haloalkane, I dehydrohalogenate. This you must know. Specifically, dilute base, hydrolysis, substitution. Concentrated base, it is dehydrohalogenation. That definitely is elimination. So these are the reaction conditions for hydrolysis family. You can see for yourself right there, mild heat, dilute solution of a strong base, potassium hydroxide. You can use this one as well, KOH, or sodium hydroxide as well. And the solution must be in water, obvious, to make it dilute. Fine. Hydrolysis were done. Okay, let me just go back just in case someone was writing this and attend to at least one person who raised up their hand. Zanelli, you're the first one. Go ahead.
Good morning, sir.
Morning, how are you? Great.
Morning. I just wanted to ask, with regards to the acid catalyst, does that mean that the acid catalyst does not in any way affect the product of the equation?
Good question. An acid catalyst, or rather a catalyst in general, its work or its purpose is to increase the rate of a reaction without affecting the reaction itself. In other words, it's not involved in the product part. All it simply does, it provides, and this is under the topic rates of reaction, it provides an alternative route with a lower activation energy. So it doesn't interfere in the product. If it is specifically a catalyst, it doesn't interfere. So it just speeds up the rate of a reaction, that's all, without getting itself chemically changed or changing any of the reactants or products in that instant. Good question, that one, Zanele. I'm gonna mute you. Right, let's move on to the next one quickly on under this topic of substitution. Now look at the next one, substitution there on that. Substitution, I actually put an example of this. This is another substitution reaction. It doesn't really have a name, like a strict name like the other one. So you can just call it a substitution. And what's happening here? I'm reacting an alcohol, there you are, with a hydrogen halide. There's my alcohol there. This is actually a tertiary alcohol. That's the first part of this topic, introduction to organic chemistry. It's a tertiary alcohol. So what's happening? The Cl replaces the OH. The OH goes to where there was Cl. Look at your product. So where there was OH, there's now Cl. And where there was Cl, I put OH and it gave me water. So that's another example of a substitution reaction. Alcohol plus hydrogen halide at room temperature. This is room temperature, about 25 degrees. We form a haloalkane and water as well. So like I said, this is a tertiary alcohols. They're converted into haloalkanes using HBr or HCl at room temperature. So it's very important that you get this right. So formation of haloalkanes from an alcohol. Okay, finally, let's go to the last one, still under substitution. This one is interesting. My first question, or my second one, if I'm not mistaken, will involve this last reaction that I'm going to talk about now. My first or second question will involve this last reaction that I'm going to talk about now. Check this out. Okay, the last one. Okay, I hope you guys can see this. I've started sharing the screen again. There you are. Okay, formation of haloalkanes from alkanes. Right, Mashoko, you got your hand up. I'll come to you. Let me finish this up. Alkane plus halogen. Okay, alkane plus halogen. Let's have an example. Methane, halogen. Let's have it as Cl2. Maybe let's have it as Cl2. Listen to me very carefully. This reaction is between an alkane and a halogen. Now, don't mix those two. I did a reaction where I reacted an alkene with a halogen. I called it halogenation. And it made sense to me because alkene has a double bond between carbon atoms, and you're adding into a halogen, right? Or you're adding a halogen. That's fine. Addition happens on double bonds. Alkane is single bonds. You can't add, you can substitute. So in this reaction, check. You've got CH4, okay, Cl, Cl. Now, one of the Cls, one of them, will substitute an H. There you go. Instead of having an H, got a Cl. And the H goes to where there was Cl, HCl. Okay? Now, this reaction happens in the presence of excess, a lot of chlorine in this example, a lot of halogen. So the reaction goes further. Look at how interesting it becomes. So look at this. So I've got Cl there, and I still react with excess chlorine. There you are, chlorine there. And again, the chlorine will take out one H. So this chlorine, let's say it takes out this H. Okay, what do I have? I already had that one. Okay, then I've now a Cl there. Plus that H that went out, it went to this Cl plus HCl. The reaction keeps going. It keeps going. So you now have this, okay, interesting, right? The H's are there. Still excess, lots of them. Each Cl takes out one H at a time. Let's say I take out this H here, there's now Cl plus HCl. The reaction keeps going until you've removed all the H's, until you've removed all of them. So you come here from methane and chlorine, you form chloromethane. You come chloromethane plus chlorine, you form dichloromethane. You come here at the end of the day, dichloromethane plus chlorine, you form trichloromethane. If you were to go further with this reaction, if you were to go further, let's say you add Cl again, that much of the chlorine there, add a lot of it. If you were to go further, Cl and Cl, you'd form the following product. They are tetra. Tetra means 4. Tetrachloromethane. From chloromethane, dichloromethane, trichloromethane, tetrachloromethane. This reaction happens in the presence of UV light, ultraviolet light, simple sunlight, or you can say the sunlight, because that's where we get our UV on Earth here. That's the reaction. An example of a particular substitution. I'm done. We're left with about over 30 minutes, so we can utilize this 30 minutes quite well. Remember, our lesson is about 2 hours, and I had to make sure that you understand everything and say quite a lot of things. All right, let's go to the questions. I have the questions with me here. Let's go to the questions. All right, I want to take this out. There, this must go. There you are. Okay, and I want to stop there. All right, Mashogo, you got a question? Please ask it. I've unmuted you. Go ahead, try that again.
Good morning, sir.
Morning.
How are you, sir? Sir, can we go to cracking, where we have 10 carbons and 22 hydrogen? Cracking reaction.
Cracking.
Yes.
Let me try and see if I can reshare the screen. Cracking is giving you, is cracking your heads, eh? It's cracking you guys big time. Right, there you are, cracking. 10 hydrogens, 22, 10 carbons, 22 hydrogens. There we are.
Okay, sir.
Talk to me.
So we have the product as 8 carbons and 2 carbons. So
no,
what if
8 carbons?
So, yes.
Okay, go ahead. Let me catch you. Go ahead, sorry.
Okay, so we have 8 carbons plus ethane, which is a double bond. So what if I say we have 5 carbons and we have 5 carbons? Will it be correct?
Yeah, that will be correct.
Yes.
So then this you get H11, and then you got H11 there. That's fine.
Yes.
Right?
Okay, thank you.
So you will prove the same thing. In the exam, they actually give you, and I'm going to do a question like that anyway. They actually give you the products, and then maybe they may put, like for example, they may do this. Let's say we didn't know that this was that. They may put X, then they say, what is the formula for X? So in my head, I must say to myself, okay, so I've got 10 and I already have 8, so X must have 2, C2. I have 22 and I already have 18 that I've broken down. And then to make it into 22, I must have 4. So X will be C2H4. So that's what they do in the exam, usually. They just show it to you like that, as you asked it and all. Bali, you got a question there? I want to unmute you. Thank you so much for that one. Beautiful.
Thank you, sir.
Hi, sir. I wanted to ask for the formation of haloalkanes. Now that we have tetrachloromethane, can we go further than that?
No, you can't, because there's nothing else to substitute. Remember, you're substituting an H. So once you get rid of all the H's, there's nothing else you can do about that.
Oh, okay. Thank you, sir.
You're welcome. All right, let me move here. There's family. Okay. All right, beautiful. No problem. All right.
Okay.
Let's go to questions. Let's go and do questions. Okay, I'm ready. Here's my first question, 2013 November paper 2, question 5. I sent this on the WhatsApp groups that are there. Those that have my number, I asked you guys to actually contact me, and you have this. I'm going to start with this question very quickly, move on as far as I can, so that at least all of us are covered in what we are doing. Here we go. Two straight chain compounds, P and Q, each have the following formula. P, C4H10. Just by looking at P, I can tell you that P is an alkane from the formula. And the name of that alkane, P, is butane. Q, C4H8. Again, by looking at the formula, I can tell you that Q is definitely butene. That's what it is. I start with 5.1. Write down the name of the homologous series to which Q belongs. Q. So Q belongs to alkenes. That's the name of the homologous series. Can start writing. Have your books by the side, guys. Let's keep this work. So 5.1 alkenes. Those that don't have the handout, I'll put my number at the end of the lesson there. Should be able to see it. Send me a WhatsApp message. I'll send you the handout as well. But for now, you can use the screen. 2013 November paper 2, question 5. 5.1, name of the homologous series to which Q belongs. Q alkenes. 5.2, compound P reacts with chlorine, K, to form 2-chlorobutane. Interesting. Write down a balanced, write down a balanced chemical equation using capital letters, molecular formula for the reaction that takes place. I told you I'm going to do this question. 5.21. We need to write down a balanced chemical equation using molecular, not structural, molecular formula for the reaction that takes place. So compound P, let me write it here. Check this out. Compound P is C4H10. I'm reacting it with chlorine. Chlorine is diatomic Cl2. So what is this? It's an alkane reacting with a halogen. The name of the reaction is substitution. It's not addition, it's substitution. Because my alkane, C4H10, has single bonds. And this is the molecular formula. And the question then says to me, write down a balanced chemical equation. So what happens? So if it's substitution, we notice from my last example of reactions that Cl will go and take out one H from C4H10. And then where there was the A, one of the H's is gone, I'm going to replace that or substitute that with a Cl, and that H that I replaced goes to where there's the other Cl. Look at this, This becomes C4, okay, H9, all right, Cl plus HCl. That's the 3 marks. And it's balanced. Check. 4 carbons, 4 carbons. 10 hydrogens, 9 plus 1, 10. 2 Cls, Cl2, there's a Cl and a Cl. This is a substitution reaction. 5,21, that's your answer for 5,21. You let me know again if you don't get something. I'll be able to explain to you guys as much as I can. Let's go, family. Let's break it down. 5.22. 5.22. The type of reaction that takes place. So obviously, it's substitution. And remember, I say to you, this one also doesn't have a name. So you can just call it substitution. Right, 5.23, we're going further. 5.23. It says to me, one reaction condition other than the solvent needed. So other than the solvent needed, what other condition do I have? So if you go back to the handout that I sent to you, or rather the document that I was using to explain myself, I made it clear to you guys that you for this reaction, for this substitution reaction, when you react an alkane with a halogen, you just need sunlight, or specifically UV light. So 5.23 UV light. Babsi, you got a question there I want to deal with you there. I'm muting you right now. Go ahead.
Okay, sir. In class, you told us that when the ask what kind of reaction takes place, you can't just say substitution, addition, or reaction. So for substitution, can we just write substitution? But when it's addition or elimination reaction, we have to specify what addition or elimination reaction it is.
Good question. Now, I say to you, when it comes to substitution, I dealt with 3 substitution reactions, and only one of them has a specific name, only one, right? The other 2 don't have. So because of that, just simple call it substitution, right? So it's a substitution reaction. Other reactions, whether elimination or addition, they have specific names. I actually want you to specify those names. Don't run away and say it's addition. What type? Hydrohalogenation. What type? Halogenation. What type? Hydration. So specify exactly. So whenever there's no name, just give the group name. Substitution. That's always the easiest thing to do. All right. Thank you so much for that one, Papsi. Let's go further. Okay. 5.3. This is where it gets interesting. Compound Q takes part in reactions as shown in the diagram below. Compound Q is C4H8, and then it's going to react with bromine to form 2,3 dibromobutane. And also in reaction 1, it reacts to form C4H10. Then it says here in 5,31, write the structural formula of 2,3 dibromobutane. Let's get this clear. Let's go. So 2,3 dibromobutane. So in my example here, I'll have it this way. 1, 2, 3, 4. This is under the subtopic naming of organic compounds. 2,3 dibromo. So on carbon number 2, I can put a bromine. On carbon number 3, I can also put a bromine. Let's call this 2,3 dibromo. Remember, in this case, I'm just counting from the left-hand side. You can do it either way. It's going to give you the right answer, whether it's count on the left-hand side in this example or on the right-hand side. So this becomes the structure of 2,3 dibromobutane. Please, family, please, guys, please, when you're doing this, don't forget to put H's. They're really sensitive about that. Remember, I'm just using this for time. But other than that, don't forget to put H's there. So that becomes the answer, and that's beautiful. Right, 5.32. I like 5.32. 5.32 says to me, the IUPAC name of compound Q. Now, at first glance, you may think that compound Q is just butene. But maybe you're not specifically correct, especially now that we consider that you reacted compound Q with bromine, a halogen, and you formed 2,3 dibromobutane. So in this case, let's specify. The reaction happening here is you are reacting an alkene with a halogen, and you're going to form a haloalkane. That's what you're going to form. And we know the name of this reaction is halogenation. Halogenation. Now the question is on Q. And they said, what is the name of Q? I want to start off with the structure of Q, but I can tell you the name of Q. Now the product that is formed is this one. That's the product. So how did I form this? I must have reacted Q, the alkene, with bromine, as you can see, and eventually I got myself into this haloalkane. So I must have added. Who did I add? Bromine. How many bromines are there? Diatomic, 2 of them. I added them on this carbon and on that carbon. So before I added them, there must have been a double bond somewhere there. And there's my double bond. And the name of this one becomes but2ene. That's the answer for Q. but2-in. Just by looking at the structure of the product, I can tell what the reactant is. Because I remember that if my BR was there, let me take out that one there, that one there. Yes, if my BR was there, then it means I must have added onto these 2 carbon atoms, because addition strictly happens on the double bond. So where there is BR and BR, that's where there was my double bond. That's why I put it there. And for me, it becomes but2-in as a name. As a structure, this one. As a name, that one. Pearl, you got your hand up. Let me help you. Go ahead. Pearl, go ahead. I've unmuted you. Not so sure if it's working or it's something on my part. Yeah, you're unmuted.
Hello, sir.
Yeah, there you go.
Hello, sir. Can you kindly repeat 5.3.3? I didn't get you.
5.3.2, right?
Yes. Yes.
Okay. No problem. Let me do it this way. Okay, here's your product. 1, 2, 3, 4. There. Here's a product, it's a haloalkane. That's what they told me. It's a haloalkane. BR. What did I add? I added bromine. To who? To Q. So the question is, what is the name of Q? So if you're adding onto something where you've got 2 substances and you end up with a single compound, that means that this reaction is known as an addition reaction. Specifically because they're adding a halogen, it's halogenation. But I want Q. So let's work backwards. So I'm adding onto the double bond. Okay, so Q must be like this. I'm adding onto the double bond. And where's the double bond? Where there's the BR. That's why I added my BRs on the double bond. So I've got a structure like this. Now let's see if it works. There, it's my double bond. And I would have been clear if I had added my BR there. The BR goes there and the other BR goes there. So Q is a name, but2-in. That's the name of Q, but2-in. All right, I'm hoping that's clear, Pearl, on your part. And for everybody else, you can write this down. That's very interesting. So we're working backwards. So in other words, you're just playing around with this and working backwards. Let me go further on another question there with you. Okay. All right, let's go back to what we're talking about. So 5.32, we said but2-in. Let's go to 5.33. Balanced equation using structural formula for reaction 1, and that's 4 marks. All right, for reaction 1. What's happening in reaction 1? I'm coming from compound Q to compound P. C4H8, that's compound Q. C4H10, that's compound P. So I'm coming from an alkene to an alkane. I can tell you what the name of the reaction is. The name of the reaction is hydrogenation. I've actually answered 5.34 because I'm coming from an alkene to an alkane. Let's use structural formula. Go with me. So alkene, I now know what it is. I drew it in the previous one. HP, I see your hand, and I'm going to attend to you right now. Let me just finish this up quickly so that at least we can cover quite a lot. What am I reacting it with? I'm reacting that with hydrogen. That's the only way I can form an alkane from an alkene. There you are. So now I came from that. From that, I've added my H, hydrogenation. That's the name of the reaction. Hydrogenation, like this, right? So you can see for yourself. There you are. You can draw that one there. That becomes your 4 marks. Structural form. Don't forget to put the H's, family. Don't forget to put the H's. From but-in, from but2-in into butane. 5.33. There. 5.34. Type of reaction that occurs in reaction 1. I think that's what I don't know Babalo or whoever was asking me about this. But type of reaction that occurs in reaction 1, obviously, is hydrogenation. If you say addition, it's still correct. Technically, it's still correct. Why I want to run away from that? What if the question was phrased like this? What type of addition reaction is that? Now you're stuck. So that's why I'm insistent that you know the actual type of addition. So give the name. Don't say it's a human being. Don't say it's a boy. What's the name? Kolani. So specify what exactly it is. 5.34, we're good to go. Right, taking this out. HP, I'm on you right now. There you go. Go ahead.
Sir?
Yes, HP?
You see how for the previous question, they were like, it's C4H8.
Okay, I can't hear you properly. Let me try and increase my volume. Maybe you can just increase yours as well and get closer to the mic or whatever you're using.
Can you hear me now?
Go ahead, yes.
See how for the previous question, they were like, it's C4H8.
C4H8, yes.
And then, but when you answered the IUPAC name, you specified where the double bond was.
Yes, I did. It's because I was able to specify where the double bond was because they told me the reaction.
If my answer was just butene, was it going to be wrong?
You'd be wrong. It's not butene. Butene suggests that the double bond is on carbon number 1. And in this case, because of this reaction, it's not carbon number 1. It's actually carbon number 2. That's
but
why
why would they ask us the question where they require you to like analyze the whole thing, if I could say?
You're saying what? I didn't get that.
Why would they ask us like a question whereas I first need to look at compound P and dibromobutane?
It's because C4H8 can be written in 2 ways. You can write it as but1-in or butene, same thing. Or you can write it as but2-in because these become positional isomers. So C4H8 as a molecular formula has 2 structures. It has but1-in or but2-in. Because they gave us this reaction where you're coming from compound Q to 2.3 dibromobutane, you can actually tell which one it is for Q. It is but2-in. It's not butene or but1-in because the double bond is the one that is broken on carbon number 2 right there. That's why you added those 2 BRs there. So you can't just by looking at a molecular formula tell what the name of the structure is. Let me give you an example of this. Look at this. C3H6O2. If I ask you what the name is here, you can say, it's a carboxylic acid. But I can also say that no, it's not just a carboxylic acid, it's also an ester. Actually, it's got 2 names for an ester. This thing has got 3 names. First thing, propanoic acid. Next thing will be methyl ethanoate or ethyl methanoate. So you can't just by looking at a particular formula tell the specific name. You can tell the homologous series, but not its specific name unless you are told from a particular reaction. So that's very important to understand. All right? Someone's got a hand up. I'm hoping you understand that one day. Kate, go ahead.
So could you please repeat question 5.33?
5.33, balanced equation using structural formula for reaction 1. Okay. Reaction 1, we are reacting C4H8. And we know what C4H8 is now. Split 2-in. And I'm reacting that with hydrogen. How do I know? Because my product is an alkane. So for me to come from an alkene to an alkane, I must have reacted that with hydrogen. That's the only way. Alkene plus hydrogen gives me alkane. It's an addition reaction. It's hydrogenation. That's basically what it is, right? Hydrogenation. All right. So that's it. That's it, Katie, on that one day. All right. Beautiful. I'm on my next question, guys. Allow me to go to my next question. Let me do maybe 2 more questions, then we'll call it a day. Our time is already almost up there. All right, same thing, 2016 Limpopo, right? The title for this question and the page number is on page 2. I'm going to do that one with you, family. Let me do this one and my last one, and then we call it a day as a family. You guys have been wonderful. I see on the chat group, you guys have been talking, and I think you're just helping each other out, and that's just great. The flow diagram below shows how 2 organic compound X and Y can be prepared with but1 as the starting material. So they've already told you but1. There you have it. Write down 4,11 says for reaction 1. So I look at reaction 1. Write down the type of reaction that takes place. So in reaction 1, I've got but1, and it looks like I'm reacting it with HBr. It's going to form compound X, and they say major product. And the question says type of reaction that takes place. Because it's but1, it's an alkene. I'm reacting it with HBr. Alkenes undergo addition. And when you react an alkene with a hydrogen halide, HBr in this example, the name of the reaction is hydrohalogenation. If you say addition, are you correct? Yes. Is it advisable for me personally? No. You need to specify what it is. So it's hydrohalogenation, 4,11, hydrohalogenation. We go further, 4,12. The balanced equation for reaction 1 using structural formula, 4 marks. All right, here we go. Let's break it down together. Here's the structure. So you've got 1, 2, 3, 4. That's definitely but1. Let me just mute Katie here. Okay, I've muted her. Right, and let me just put the double bond on carbon because it's but1 on this carbon here, and that's okay. So I can put that, and then that, and then that. Remember, around every carbon atom, there must be 4 bonds. What am I adding? I'm adding HBr. What did I say when I made the example? When I was teaching, take the H, where does it go? To the carbon in the double bond containing the most number of hydrogens. So this H goes there. Where does the Br go? To the carbon in the double bond containing the least number of hydrogens. They want the structure. 1, 2, 3, 4. I need to add. I am hydrohalogenating. It's an addition reaction. My Br, there you are. And I've also added my H, and that becomes the structure. So 4,12, that becomes the structure from an alkene to a haloalkane after reacting with the hydrogen halide. So that's compound X. Please don't forget what compound X is all about. Let's go to 4,13. 4,13. It says the IUPAC name of compound X. Judging by what I'm looking at, compound X is 2-bromobutane. Guys, again, naming is part of this topic, right? Today I'm just specifying only this part. So there are other topics, there are other parts to this whole thing of organic chemistry. So it's 2-bromobutane. There you are. That's the name, 4.13. Please write this down, guys, in your books. Make sure that you get this right. I have the memo for this. So after the lesson, I'll probably send it to the WhatsApp groups. If you're not in any of my WhatsApp groups, just send me a message. I'll add you in and also get you the memo right there. Linde, KH, go ahead. You've got a question.
Yes, sir. 4.1.2, sir. What if they said they wanted a minor product? Would it be the same minor product? Need to say
no, but, okay, good one. They wanted a minor product. then the Br would add onto the carbon with the most number of hydrogens. We do the opposite.
Oh, okay.
So the Br will come here, but they don't do that. They ask you for major, but the Br would come here, just to answer your question. And then the H would go there, where there's the least number. That would be your minor product. Okay, but remember it's major, so therefore if the Br goes to the carbon in the double bond containing the least number of hydrogens, the H go to the carbon in the double bond containing the most. Good one, thank you. You can mute yourself. Right, let's go to my next question there. Okay, I moved too fast here. There you are. For reaction 2, interesting. So let me just have compound X close by to me so that at least everything of mine is fine. I need compound X close by. So compound X is 2-bromobutane. So there you are, I need him. So let me just have him close by there. It says now in 4,21. For reaction 2, write down the type of reaction that takes place. So reaction 2, they're coming from compound X, dilute base, and heat. Dilute potassium hydroxide, it's a base. Sometimes they use sodium hydroxide. And then reaction 2, you're coming from a haloalkane, and you're reacting that with a dilute base in the presence of heat, 4,21, type of reaction that takes place, definitely hydrolysis. Definitely hydrolysis. That's 4,21. 4,22. We go. 4,22. Structural formula of compound Y. Structural formula of compound Y. Now, hold on, family. Check this out. So this is compound X, and then Y. What happened? You reacted that with potassium hydroxide, but it was dilute. And because it's dilute, we gave the name hydrolysis. Hydrolysis is a substitution reaction, right? And they want, in this case, the structural formula of compound Y. So in this case, I will make sure that I substitute. So where there is Br, I'll just put an OH. And then further on, I add my situation like that. And I'm good. I'm fine with this. So this is potassium hydroxide, all right, which is a dilute base, substitution, hydrolysis. So that's the formula, structural formula of compound Y. So Y is this. I substituted. So that's why. Write it down on the side, guys. Just want to make sure that it's clear to everyone. The name, 4.23, interesting. It says IUPAC name of the positional isomer of compound Y. IUPAC name of the positional isomer of compound Y. Positional. Just think. A positional isomer, they've got the same molecular formula. They belong to the same homologous series. In other words, they've got the same functional group, but there is a difference in the positioning of that functional group. So if I look at compound Y, the functional group, the hydroxyl, is on carbon number 2. Its positional isomer must have the functional group hydroxyl on carbon number 1. So for 4.2.3, I would have it this way. So positional, instead of putting the OH on carbon number 2, I put it on carbon number 1. The position of your particular functional group, which is the hydroxyl, in this case, has changed. So positional isomers, how do they differ? They differ in the concept of the position of the functional group. In Y, it was in carbon number 2. In its positional isomer, it's in carbon number 1, the OH. So that's the structure of the positional isomer. Let's go further, people. Let's break it down together. Let's go further. All right. Okay, so that's 4.23. Let's quickly go to 4.3. Says write down the, I'm reading, it starts here. Concentrated sulfuric acid is added to compound Y and the mixture is heated. So let's look at Y. Okay, so Y, the alcohol. Concentrated sulfuric acid is added to compound Y and the mixture is heated. So alcohol, and then I'm adding, or rather I'm reacting this with sulfuric acid, and you heat the mixture. Then it says, write down the structural formula of the major organic product formed 2 maps. I need to think. Compound Y is an alcohol. Whenever an alcohol is in the presence of sulfuric acid, that reaction is dehydration. I must remove water from the alcohol. Somebody asked me a question about, oh, does the sulfuric acid interfere in the reaction? I said, no, it acts as a catalyst. And that's true. Right in front, just by reading the question, it acts as a catalyst right there. So in this case, break it down with me. You've got compound Y, which is this one. 1, 2, 3, 4. And on carbon number 2, I've got an OH, and I've got an H there. And I'm reacting this compound Y in the presence of sulfuric acid. And I just say to you, I definitely must get an alkene, dehydration. I'm going to remove the OH, there you go, and the H, there you go, on the right-hand side. So in this case, I'm forming my major product. These guys are gone. And what do I replace by the double bond? And so your structure would look something like this. So it says in 4,3, write down the structural formula of the major organic product formed. This is the major organic product formed. So that's 4.3, as you can see. So remember that, guys. Make sure that you understand all of these things over and over again. Okay, I'm ready for my next one there. We're about to finish our lesson anyway. Okay, all right, here we go. So write down, so that's 4.3, that's the product, major product formed. Let's go to 4.4 quickly, 4.4. Reaction 2 is now repeated using concentrated, KOH. All right, I'm gonna go back to reaction 2. Reaction 2 is now repeated using concentrate. So it's no longer dilute, it's now concentrated. All right, let's think about this. Right, it's no longer dilute, it's concentrated. I say to you, when you react, right? When you react, and you're reacting with a dilute, you hydrolyze. You're reacting with concentrated, what do? Dehydrohalogenate. Concentrated. Here we go. I'm reading the question again. So reaction 2, and the question says, homologous series to which the major product of this reaction belongs. So let's get it clear. Whenever you react compound X, which is a haloalkane, by the way, and you react it with concentrated potassium hydroxide, it's going to give you an alkene. That's the major product. So the alkene is the one, the homologous series. The major product is an alkene. So for question 4,41 is just alkene. 4,41, alkene. 4,42, names or formulas of the inorganic product formed. Names or formulas of the inorganic product formed. Now, I like this, inorganic product formed. Now, let me take it back to a previous screen, right? Where is that? Dehydrohalogenation. Okay, follow my lead. Look at this. Now, I explained under dehydrohalogenation that you form an alkene, which is what we answered on 4,41, and then a metal halide and water. So the organic product is this one, alkene. Then these two are the inorganic products. They are the inorganic products. So to answer our question that we're dealing with right now, And I'm going to go back to the question quickly. To answer that particular question that says names or formulae of the inorganic product formed, 2 marks. Since you are reacting with potassium hydroxide, so your metal halide in this case, right, will be, check this out, and annotate this. So remember, X has a bromine in it, and you're reacting with concentrated potassium hydroxide. So then the K will mix out with the Br and it forms KBr. That's the metal halide. The OH will mix up with the H that has been removed. Remember, it's dehydrohalogenation, and it's going to form water like this. So these are the 2 products, KBr. If we were using sodium hydroxide, it would be NaBr. But because we're using potassium hydroxide, it's KBr plus the water. Those are the 2 products that you end up forming at the end of the day. All right, beautiful. So your answer for 4.42 is KBr, which is, the name is potassium bromide, and water, the name is water, the formula is H2O. All right, so they say name or formulae. All right, beautiful people. All right, let me stop here. Let me stop there. Okay, I got another class coming up right now, so I need to leave. Okay, family, guys, have been really wonderful, and thank you so much for coming through on this one, right? And I think I see a number of questions on the chat there, and I wasn't able to pull through. Those that still have a question or something, please ask me now before I end the session, because I see a lot of discussions, and that's beautiful, and I love that. You guys have been really, really wonderful. Now, I'm going to upload this on my YouTube channel, and I'm going to write down the name of my YouTube channel. It's Mr. X, you can write it down, Mr. X Mathematics and Physical Science, grade 12. Mr. X Mathematics and Physical Science, grade 12. In that particular YouTube channel, I have uploaded a lot of videos, right? So you guys can check them out, those videos. I do math as well, so I've uploaded trigonometry, just a part of it, and all that. Listen, guys, because this lesson that we're having is attended by almost a lot of people from all over South Africa. So some of you are asking me, so say, do you do extra lessons, blah, blah, blah. Yes, I do. I actually do extra lessons, right? And on Sunday, I'm having an extra lesson, and I just want to make sure that I show you what I'm going to be doing on Sunday. Where's my stuff there? Right, so this is what I'm going to be doing on Sunday, there. So on Sunday, I'm going to be doing math at 9 o'clock to 11 o'clock, Euclidean geometry, part 1. I'm going to deal with the grade 11 part of it, which is coming out in your final exam, and part grade 10 as well. The other week, I'm going to do part 2, and then there's also part 3. Then physical sciences, I'm going to be doing acids and bases, part 1. But these classes are paid for. This one was free. It was for you for a youth day. These ones are paid for. It's 150 rands. It's a group class. 150 rands for a 2-hour session. So I will do these ones here on Sunday. So if you're interested, there's my number. You can just WhatsApp me, and then we take it up from there. So a lot of people come through for that one, and they get help. So Euclidean geometry part 1 on Sunday, this Sunday, 9 o'clock to 11. Then physical science 3 to 5, acids and bases part 1 as well. I am on Instagram under the handle Mr. X Math Science. I'm going to do a video on Friday, time permitting, on functions and graphs. I'm going to teach you how to transform graphs from an equation. A very critical part, things like h of x is equal to f of x plus 2 minus 3. Describe the transformation, f of minus x minus f of x. How about 2f of x? All those kind of things. I'm going to do that, but I'm going to upload it on my Instagram, so you can like and follow that page as well. On Facebook, I am under Beacon of Light, Mathematics and Science Center. The picture is just a B, simple B, and that's my cell number as well. So if you're interested in all that, you just come through and let me know. All right, I need to finish up the section here, but I need to give over to Umpo, and then Umpo has a question, and then from there on, we can say our goodbyes. You guys have been really wonderful. Umpo? I've unmuted you. Mpo. Let's try that
Can you hear
again.
me?
Now I can.
Okay, so can you please repeat 4.3.3 because I didn't understand how is it a major product formed from the second hydrocarbon?
4.3.3 or 4.2.
4.2.3. 4.3, say 4.3.
Write down the structural formula of the major product formed. So you're coming from
Yeah, I
compound Y. It's okay. Let me take you through, don't worry. You're coming from compound Y, so you let me know if you don't understand something. So what is compound Y? Compound Y is this one. Yes, where the OH is on carbon number 2, right? And the question says, you are reacting this with concentrated sulfuric acid there, trying to make sure that it stands out. And in a reaction of an alcohol in the presence of concentrated sulfuric acid, that reaction is dehydration. So in other words, we're going to remove an OH and an H. So it becomes like this, the major product, the double bond there, like that. So, and the question then says, homologous phase to which the major product belongs to. It's an alkene. There's a double bond between the carbon atoms. So that's how it looks like. Is that okay?
Yes, sir. Thank you.
You're very welcome. All right, family, you guys have been really wonderful. I gotta end the session right now. I'm gonna upload this on my YouTube channel within the next hour or so that at least every one of you can be accommodated. Please, guys, I'm gonna stop the recording now. People are saying thank you, say hi, thank you now, thank you so much. You guys have been wonderful as well. I'm gonna stop the recording now.